Everyone, welcome my channel Electrical Network Learning. Today I speak about the resonance of electrical circuit. The first of all, resonance is apply RLC circuit. It may be a series circuit or it may be a parallel circuit. So resonance is two types. One is a series resonance and another is a parallel resonance. So first of all, I describe about the series resonance. What is series resonance? So in this figure you can see that this is the RLC series circuit and voltage drop from the resistance, inductance and capacitance is equal to VR, BL and BC. So in this RLC series circuit, when circuit current 180 degree apart in phase with the applied voltage, the circuit is said to be series resonance. So the series resonance you can derive or describe from impedance Z. So Z is equal to R plus J omega L plus 1 by J omega C. So from this here, the resonance condition arise in the series RLC circuit when the inductive reactance is equal to the capacitive reactance, means XL is equal to XC. So a series resonance circuit has the capability to draw a heavy current and power. That means the circuit is otherwise called the acceptor circuit. So from this equation you can find what is the value of Z. Z means impedance. So Z is equal to R plus J into omega L minus 1 by omega C. 1 by omega C. So that implies what is the result of impedance Z? So Z is equal to R plus J into XL minus XC or XL minus XC, that is called the X. So X means reactance. So what is the XL and what is the XC? So XL is equal to inductive reactance and XC is equal to capacitive reactance. So from this figure or from this graph you can notice that when impedance is minimum then current is maximum. Why? Because I is equal, you already know I is equal to V by R. So from the resonance condition R is equal to Z. So I is equal to V by Z means I is inversely proportional to the Z. So when I is maximum, then impedance is minimum. Why I is minimum, then impedance is maximum. So in this series resonance, current is maximum. So impedance is minimum. So from this figure, the supplied voltage or supplied the supply is increase the inductive reactance decrease increase or capacitive reactance decrease. So at the low frequency capacitive reactance is infinitely large and frequency is increase. So in this reactance Xc is decreased rapidly but never becomes zero. Similarly, in low frequency inductive reactance starts from the zero, increase linearly with frequency, then the total frequency is how much or total reactance is how much? So total reactance means X. So XL minus XC is equals to 0. So that implies what? Now XL is equal to XC. So at the low frequency, XL is less than XC. It is purely capacitive. When in high frequency XL is greater than XC, this is the purely inductive. So when XL is equal to XC, it is the resonance condition. At that time the impedance is equal to purely resistive, means Z is equal to purely resistive because its value is equal to 0. So from the series resonance current is maximum then and impedance is minimum, so this circuit is purely resistive. So from this here XL minus XC is equal to 0. So that implies what is the value of XL? XL is equal to omega 0 L and XC value is 1 by omega 0 C. So omega 0 L minus 1 by omega 0 C is equal to 0. So omega 0 L is equal to 1 by omega 0 C. So what is the value of omega 0 square? Omega 0 square is equal to 1 by LC. So omega 0 is equal to 1 by LC root over. So what is the value of omega? Omega is equal to 2 pi f. So what is the value of 2 pi f? So 2 pi f is equal to 1 by LC. So what is the value of f or f0? So f0 is equal to 1 by 2 pi LC root over. So this f0 is called the resonance frequency. So from the series resonance, the what is the value of resonance frequency? So resonance frequency F0 is equal to 1 by 2 pi LC root over. So in the resonance, cos phi means power factor. So cos phi is equal to R by Z. So R by Z from this here, Z is equal to R. So cos phi is equal to R by R is equal to 1, means power factor or cos phi is equal to unity. So these are the resonance condition from the electrical circuit. So what is the effect from the series resonance? So at the series resonance, the resonance condition XL is equal to XC, the impedance of the circuit is minimum and it reduces the resistance of the circuit Z is equal to R. So next, if the resonance condition, the impedance is minimum at the current in the circuit, so this is the maximum. So I is equal to V by R or V by Z. So as the value of the resonant current I maximum, hence power factor is how much? So power factor P is equal to I square R. So power is equal to P is equal to I square R, but power factor is equal to cos phi is equal to 1 or unity. So at the resonance condition, current drawn by the circuit is very large, or we can see that the maximum current is drawn. So therefore, the voltage drop across the inductance L is equal to VL. So VL is equal to how much? VL is equal to IXL. So I into 2 pi FL. Similarly, when the voltage drop across the capacitance C, so that is VC. So VC is equal to IXC. So I into 1 by 2 pi LC, 2 pi FC. So these are the very large amount of in electrical circuit. So this is the effect of the series resonance circuit. So lastly you can tell that omega 1 and omega 2 respectively below from the resonance frequency omega 0, and which current in the circuit becomes the 7.707% of current maximum. So current from the resonance condition is equal to I1 is equal to I2 is equal to how much? Now I0 divided by 1 root 2. So I1 is equal to I2 is equal to I0 by root 2. So from this here you can notice that when current is 90-degree leading, so VL is less than, sorry, XL is less than XC. So from this graph you notice that 90-degree lead, so this is XL is less than XC. When 90-degree lag, so XL is greater than XC, and when it is phase or angle is equal to 0, so XL is equal to X. So this is the three condition of resonance circuit. So this is the series resonance of RLC series circuit. Thank you.